So chemical reactions is now going to be sort of the culmination of all the things that we've done up until this point. So we're going to be coming back to, which was just like last week, or 2 weeks ago, chapter 5, with all the nomenclature stuff. That's important now, because that's how we're going to be able to recognize different chemical compounds and combine them into the correct chemical formulas. We're also going to be using, actually in the next chapter, using molar masses to convert between grams and moles of things and how that relates with chemical reactions. So a lot of the stuff up until this point has been putting together the little pieces, and now we're going to take those pieces. It's like building anything with Lego, right? Sometimes you build a lot of different parts, and then we're taking some of those parts now, stacking them on top of each other. So one of the classic chemical reactions, because we sort of talked conceptually about what chemical reactions are. The classic one is you mix baking soda with vinegar, so acetic acid is this compound, and it forms CO2 gas, water, and sodium acetate. Usually you put a little soap in there for extra bubbles, but that doesn't react. So then when you add these things together, you get the volcano erupting, spilling over your mixture. So this is one type of reaction. And so that's kind of how we're going to work with these. We're going to fit them into different categories. And this one is a gas evolution reaction. So it's reactions that occur in liquids. So you mix two liquids together, or you mix some things together in a liquid, and it forms a gas. In automobiles, right, every car, well, aside from electric cars, gas-powered cars are, what, a phone call from Los Angeles? It's probably a scam. If it's important, they'll leave a message. Yeah, automobiles are giant metal boxes powered by explosions, right? So those explosions are a chemical reaction. It's primarily octane combining with oxygen in the air and a little bit of a spark, and then that creates the explosion. And that's a type of oxidation reduction reaction. Sort of the bigger category that those are in are combustion reactions. So oxidation reduction, we'll talk about that a little bit, because after we do chapter 7, we'll take a brief detour into chapter 16, talk about how to balance those kinds of reactions. But it involves the transfer of electrons, not just the reconfiguration of the atoms. Laundry detergents also have chemical reactions, specifically for removing hard water ions like calcium and magnesium. So those calcium and magnesium ions would interfere with the soaps and make it so they don't do a great job of cleaning. But we add carbonate, or sodium carbonate. That sodium carbonate reacts with calcium and magnesium to form two solids, calcium carbonate and magnesium carbonate, which aren't soluble in water. So they drop out of the solution, which lets the soap work better. So in this case, we have a reaction that forms a solid substance in water is a precipitation reaction. We will come back to these two. It's kind of a brief overview of where we're going. The slide could change. So if you could see, if you could really go down and see at the level of atoms and molecules, it would be really, really easy to tell if something was a chemical reaction, because you would see the molecules colliding with other molecules and rearranging to form new molecules. Not always I should say, not always the case. Not the case at all, right? We cannot see at that teeny tiny level. In fact, the act of shining light on something sometimes is enough to move it and change it, so you can't look at it because the light moves it. So we have to use other ways to identify reactions. One of those is a color change. So if you usually mix two things together and the color changes, then you're getting some sort of chemical reaction. In this case, it's like a baby spoon, and when you put it into water that's too hot, it causes a rearrangement of those molecules to change the color from red to white. So you'd know that the water, or oatmeal, I guess, would be too hot. Another one is the formation of a solid. Right? So like the laundry detergent makes calcium carbonate and magnesium carbonate. If you pour one liquid into another, and it forms a solid, and usually it's not always like, you pour water in and a rock drops out. It usually displays like this, where it's cloudy. And in this case, we're getting the yellow mixing with the clear liquid to get this red, cloudy solid. And we'll do a lab where you'll mix stuff together and see these kinds of things. So that's a precipitation reaction. Another one is forming a gas. Sometimes, I think we've probably all had this experience where you go, usually like out of a garden hose or like a tap somewhere, the water comes out and it's super, super cloudy, but then it clears up eventually. That's not a chemical reaction. That's just air that's in the water. So when you have a chemical reaction that forms gas, it'll be a continuous formation of bubbles. So you'll usually drop like an Alka-Seltzer tablet, a solid into a liquid, and it'll form bubbles, and it'll keep going, unlike the water, which just kind of clears up and stops. So it'd be a gas evolution reaction. Another dead giveaway, or 3 dead giveaways that don't have specific reactions. I think these would mostly fall into the category of oxidation reduction. But heat absorption, so it's like this chemical cold pack, or heat emission, right? So if something generates heat, specifically burning, like natural gas, or if it produces light, then those are all also signs of chemical reactions. So a burning natural gas flame produces heat and light. Chemical cold pack becomes cold when the barrier separating the two substances is broken. So it's not like, right, because if you pull something out of the refrigerator and you touch an ice cube, it's cold. But this, in case, it would be something that's warm in your hands. You break that barrier and it gets cold. Or glow sticks, which emit light when you mix the two substances aside. Again, breaking a vial to let them mix. My wife and I actually wanted to do the glow stick reaction for our wedding as like a marriage ceremony thing. You know, people do the sand? Well, we were going to mix hydrogen peroxide and luminol, but we got married in June at like 5:30, so there's no way anybody was going to see it. We did do used an indicator, so we had 2 clear liquids and it turned bright blue, so that was fun. Lab goggles and everything. So some of these things, though, like I already talked about one, can fool you into thinking you have a chemical reaction, right? So if you, like the water from the tap, or sometimes if you just mix 2 liquids together, you get some bubbles. Another case would be water boiling. Bubbles are being formed, but it's a physical process. So if you were to look at, in this case, right, we have water molecules, which are packed closely together in the water. As they heat up, they separate, but it's still water molecules. We haven't changed the chemical composition of the water. Freezing would be another one. And then, of course, because the chemicals like to be tricky, chemical reactions can occur without any obvious sign. So something could be going on and you wouldn't even see it. Actually, if you haven't already, you should go on YouTube and look up like gallium and aluminum, because you can put a little scratch on a piece of aluminum, and if you touch gallium to it, that gallium will spread throughout the whole thing, and you won't see it until it becomes like as brittle as a chocolate bar. So chemical reactions can also occur without any sign. All right, knowledge test then. Which change involves a chemical reaction? Explain your answers. Is there a brave soul? Butane burning and a butane lighter? Yeah, chemical reaction, but why? Heat. Mm-hmm. And light. So we also have light in that case. Again, anytime something's burning, that's a chemical change or chemical reaction. Butane evaporating out of a butane lighter. No. It's still butane, it's just gas. So this is physical. Or actually, I should write this as no reaction. Wood burning, chemical. Again, heat and light. Dry ice subliming. It's physical, yeah. So it's not a reaction. No reaction. Yeah, it's frozen carbon dioxide just becomes gaseous carbon dioxide. Or water if it's in your fridge. Yeah. So they can be easy to identify, sometimes not so much. But this is sort of the key of this chapter, is the chemical equation. Like I've said a few times now, we're taking these molecules, in this case methane and oxygen, and we are sort of ripping them apart and putting them back together in a new way. So we've taken these molecules, broken them up, and made new molecules from them. So this side on the left would be our reactants. And then on the right, we'd have products. Right, so that's the thing produced. These are the things that are reacting. And one key for this whole process is that we're not creating any new molecules. We're not destroying any new, or we're not destroying any atoms, we're not creating any atoms. So in a balanced chemical reaction, which this one is not, we have to have the same number of each type of atom on both sides of the equation. Because the atoms on the right side have to come from somewhere. Oh yeah, I forgot that was on that slide too, but we write often the state of the atoms or molecules in the reaction. So if it's a gas, if it's a liquid, solid, or if it's aqueous, which just means it's dissolved in water or mixed with water. So we have to balance these reactions. If you look at this one, I think maybe I'll just make it a little bigger here. On the left we have CH4 and we have O2. So each of these is representing, right, one molecule made up of these atoms. On the right side we have now CO2 and we have H2O. So if we go through and count up these oxygen atoms, on the left side we have 2, but on the right side we have 3. So this is an unbalanced chemical reaction. So what we do is we can't change the subscripts because that would change the molecule, but we can have more or fewer of each type of molecule. Because not really fewer. You can always add more though. So this equation is also unbalanced with regard to the number of hydrogen atoms. So on the left side, CH4 has 4 hydrogen atoms. But on the right side, the only hydrogens we have are in H2O, and that only has 2. So we have to balance this chemical equation. So to do that, we add the coefficients. Right? So it's this number in front to change the number of the molecules that we have, so number of whole molecules, it has to be a whole number. Right? We can't have half of an oxygen atom. So if we put a 2 here, that means that we're reacting this 1 methane, CH4, with 2 oxygen atoms to produce 1 CO2 and then 2 water molecules. I really like balancing chemical reactions, and I know that's a super nerdy thing to say, but they're very much puzzles. They will always work out if you have the chemical formulas correct. So there is a correct solution, you just have to find it. And we'll talk about the steps. So the first step is to write a skeletal equation by writing the correct chemical formulas for each of the reactants and products. And this is critical, and this is why nomenclature matters so much. So a lot of the practice problems that we're going to do just have the names of the molecules. So you have to work from that name to get the correct formulas, and then go through the rest of this process. So moving from there, once you have that, we're not going to touch those chemical formulas anymore. We're just going to add coefficients to them. So if an element occurs, and these are really just sort of general guidelines, by the way, to get you started. If an element occurs in only one compound on both sides of the equation, balance it first. If there's more than one element like that, balance metals before nonmetals. So if we go back to this to explain what that means, because it's a little wordy. So we're looking at the individual elements at this point, because we sort of balance elements one at a time. So you want to see if there's an element that occurs only once on one side of the equation. So carbon over here is only part of CH4. Carbon on the right side is also only part of CO2, but oxygen is part of CO2 and H2O. So we would not want to balance that first. So that's what it means on the left side, oxygen is part of one compound, but on the right, it's part of two. So we want to start with something other than oxygen. So that's step 2. For step 3, if an element occurs as a free element, so that means the element by itself not bound to another element. So like O2, there's 2 oxygens there, but it's one type of element. So that would be a free element. If you had iron by itself, free element. And you want to do the free elements last. And then start by balancing. Always balance free elements by adjusting the coefficient on the free element. And again, we'll do some examples. We'll do a lot of examples, actually. Then, if you get to the end of all that, and you have a fraction as one of your coefficients, you can change those into whole numbers by multiplying the entire reaction, all of the coefficients, by some factor to make it a whole number. So if you get 1/2, multiply everything by 2. If you get 1/3, multiply by 3. You get 1/4, multiply by 4. It's kind of similar to empirical formula. Because in empirical formulas, you can end up with halves and thirds and quarters. And you multiply those by the same factors to get whole numbers. And then the last and final step is just to count all the atoms of each type and make sure they're matched on each side. All right, so you should have the same number on the left in your reactants, same number on the right in products. And then do change the coefficients. Do not change the subscripts. The only time you change subscripts is when you're writing out the chemical formulas in your very first step. After that, they're set in stone. Unless you start getting into a loop and you absolutely cannot balance it, even though you've tried every possible coefficient combination, then you probably messed up on your chemical formulas. But assuming they're correct, you don't change the subscripts. Okay. So like I was saying, we have solid chromium oxide and solid carbon to produce solid chromium and carbon dioxide gas. So you need to know the nomenclature to be able to write these out. I would start with writing them out with their charges. So chromium will be our first one. What's the charge on chromium? It's a transition metal, so it forms multiple charges. And we're given the charge actually in the parentheses, 3+. And then oxide, so it's the oxygen, ion of oxygen. It is in 6A. 2-. And then that's going to be reacting with our solid carbon. That one's easy. So if you get just one element by itself, solid carbon, that's a free element. doesn't have a charge. And we're going to produce solid chromium. So that's going to be an element. And carbon dioxide gas. So it's a molecular compound. We know that because it's using the di prefix on oxygen, which means we have 2 oxygens, so CO2. Now, most of these, we don't have to actually go through and figure out what the actual formula is. But for chromium oxide, we need these charges to balance, right? Because on ionic compounds, they're always matched up, so the charges balance. This one we can do with the crisscross method. So we take the magnitude of chromium's charge, and we'll make that the subscript for oxygen. We'll take the magnitude of oxygen's charge, make that the subscript for chromium. So we'll get Cr2O3, and that is a solid. And then solid carbon. And then chromium solid plus CO2 gas. So that was step 1 of balancing. And that one's probably going to take a while at first until you get used to converting names to formulas. But we're going to do it a lot, so you will get good at it. Or you should try to get good at it, I should say. All right, so let's go back to our steps now. I believe the next step is to, if an element occurs in only one compound on both sides, balance it first. If there's more than one such element, balance metals before nonmetals. All right, so elements that occur, let's highlight these. Elements occur that only in one compound on either side. Chromium, right, is only in chromium oxide. And actually oxygen is only in one. Carbon's only in one. Chromium's only in one. Carbon, oxygen. So in this case, they are all only part of one compound. So we can say, okay, still need somewhere to start, so we'll start with the metal. So our metal here is chromium. And we can look on the left side, we have 2 chromium atoms. So we need to have 2 chromium atoms on the right side. So currently there's just 1. So we can add a coefficient of 2. So now we've got 2 chromium atoms. So now we'll go back to oxygen. We can balance oxygen next. So we're going to get O3, and we have O2. Now this is where the same trick that works for the crisscross method works here. So we take this 3, and we'll make that the coefficient of CO2. Then we can take the 2 subscript on CO2 and make that the coefficient for chromium oxide. Because when we do that, we've essentially multiplied them so that each of them is 6. So we balanced our oxygens, but we also changed the number of chromiums. So in a lot of these problems, this will happen. So really best to do these in pencil, at least the coefficients, because you will go back through and change them a few times probably. The other thing that I like to do is if we do something like that, then I'll just follow that change, right? So we caused a problem, now we're just going to fix that problem before doing anything else. So 4 chromiums now. This is 2 times the 2 chromiums. So we'll go back over to the right side, and instead of 2 here, we'll make this 4. Now we only have 1 element left to balance, which is carbon. So left side we have 1 carbon, on the right side we have 3 carbons. And we don't want to change the 3, obviously. So we'll add a coefficient of 3 here. Because if we change the 3 on CO2 to 1, then we've unbalanced oxygen And we'll end up going back through the whole thing again. Like I said, we do have a bunch of examples like this, but are there any questions at this point? Not at this point.
Not yet, anyway.
All right. That's good. All right, so our next reaction here, we'll write a balanced chemical equation for the combustion reaction of gaseous C4H10 and gaseous oxygen to form gaseous carbon dioxide and gaseous water. So C4H10, that's easy. So that's a gas. That's going to react with gaseous oxygen. This is one of the things, one of those tricky things that we talked about briefly and is now important, is that oxygen is one of the diatomic molecules or diatomic molecular elements. So it exists as O2. That'll be a gas. And if, as a reminder, that's Brinkelhoff. So each of those elements exists as a diatomic. And then we're going to have carbon dioxide, CO2, that's a gas, plus gaseous water, which is H2O. So this one didn't involve any ionic compounds, so I can just write out the formula. So where should we start in balancing this one? Hydrogen? So we want to balance the free elements last. Free elements are last, and oxygen is also part of two. So in this case, we can start with hydrogen. Like I said, those rules are really a guideline for getting you started. The whole key is make sure you have the same number of atoms on each side. Oh, I didn't do that on the last one. We'll do it on this one. All right, so hydrogen first. So if you look on the left, just because the reason I'm starting on the left, if you were curious, is just left to right. We can look at it on the left first, or we can look at it on the right first. But we have 10 oxygens on the left side. So then we need to multiply our H2O by something to get 10. So multiply by 5. Now that does change the number of oxygens, but because we have oxygen here also, and we have a free element oxygen, we're going to save that for last. So we'll come back over to the other side, and we did hydrogen, so now we'll balance carbon. So we have 4 carbons here. Then we can add a coefficient on the right side for CO2. Just make that a 4. And you could, if you wanted to, do something like this, where you say carbon, hydrogen, oxygen. If you want to keep track of this, say, all right, we balanced carbon, we've balanced hydrogen. Oxygen's the only one left that we haven't balanced yet. So we'll need to now take into account that we have oxygens here and oxygens here. So this is going to be 4 times 2 oxygens, right, because every CO2 has 2 of those. So that's 8 oxygens, plus the oxygens from water, which is another 5. Yeah, so 13 total. So how do we get 13 out of 2 oxygens? This is where we get halves. So I think the easiest way to do this is, if this is 13 odd number, obviously 2 is even, just do 13 over 2, right? That would give us 6.5. But this way we can also see that we need to multiply everything now, because we have a fraction, multiply everything by 2, and then we'll get whole numbers everywhere. So I'm actually going to move this around a little. tiny. So multiplying everything, or all of the coefficients by 2, and even in these places where don't have a coefficient written in, it's implied that that's 1. So this is going to be 2 C4H10 plus 13, because 13 times 13 over 2 is 13 gas, and that's going to be 8 CO2 plus, not 5, 10 H2O. You don't have to rewrite the whole thing, but it can be really easy, like I almost just did, miss multiplying something by 2. If you do check everything, though, so now we've got this balanced also. If you check everything, you should catch that. So now we can take this and say, okay, how many of each of these do we have? So we have 8 carbons, right, so the 2 times 4. And we have 20 hydrogens, 13 oxygens. And then on the right side, we'll do the same thing. And again, the order here that you check these in doesn't matter, but if we do it in the same order, it's easier to see. So we have 8 carbons. Then we have hydrogen next. So 10 times the 2 hydrogens in water is 20. And then for our oxygens, we have, oh, sorry, this is not 13. This is 26. Because over here we have 8 times 2, so that'll give us 16. And then 10 times the 1 oxygen will be another 10. I guess I do it like this, 16 plus 10, 26. Got to remember to multiply the coefficient by the subscript for each element. Yes, it was 13 before. But we multiplied it by 2. So we got the same numbers on both sides. We're good. Balanced chemical equation. Now, are there any questions? All right. Keep going. So now we're going to write a balanced chemical equation for the reaction between aqueous lead acetate with aqueous potassium iodide to form solid lead iodide and aqueous potassium acetate. So acetate, one of those polyatomic ions. And I always forget what its actual formula is, but that's what it looks like. So lead acetate. And a dead giveaway that this is an ionic compound is that lead has a charge. All right, so that 2 there, because lead is a transition metal, even if it is on the far right, it's one of those transition metals with multiple charges. So lead, and then acetate is C2H3O2 minus. And then that's going to be reacting with potassium iodide. So potassium, one of the consistent charges, it's in column 1, so it's a 1 plus charge. Iodide is in 7, so it's a 1 minus. And then we're going to, oops, it's not that, wait. Oh, I'm getting lost. Here we go. Arrow is here. All right, so those are our 2 reactants. Then our products, which is going to be everything that comes after it to form, is going to be lead iodide, lead here, keeping the same charge. Iodide we already found, so 1 minus, plus potassium acetate. It's a lot of ions. So now we have to make sure that these are all balanced, right? So that the charges cancel out on each of the ionic compounds. So for lead acetate, what? already balanced? Well, this one is not. So we have lead with a 2+. Acetate has a 1- charge. So we need 2 acetates to balance the charge on lead. And then potassium and iodide is 1+, 1-. So we just need one of each. Oh, I guess I should be writing, this is aqueous, aqueous. And then we're going to get solid lead iodide. So again, we have lead with a 2+ charge. Iodine has a 1- charge. So we need 2 iodines. Plus potassium. Potassium's a +1, and acetate's a 1-. So those balance. So now at this point, assuming that we've done it all correctly, solid. Oh, this is aqueous. It's AQ. So that's just pulled from up here in the question itself. Nope, should be O2. You're right. Thank you. Aqueous, yeah. Okay. So now at this point, we've got the correct chemical formulas. So we're not changing subscripts anymore. Those are set in stone. But from here on out, we're going to balance with coefficients. So I think on this one, if we look at either side, each compound or each atom or polyatomic ion, because polyatomic ions move in groups or as units, they only occur in one compound on either side. So by the conventions that we set up before, we don't have any free elements, we'll just start with a metal. Aside from not starting with free elements and not starting with things that are in 2 compounds, you really just start on the left and just try it from there. If it doesn't work out, if you feel like you get stuck in a loop, just erase everything, start from a different element or a different compound. So we can start here. We can balance lead first. But lead, and then there's 1 lead on the right side already. So we're good to go. And the way I like to do this is, now that I went from here to here, then I'll just go to iodine next. And so we have I2 and just 1 iodine here. So what coefficient do we need to add? 2. So now we balanced this. I'll say, okay, iodine is balanced. So I'll look at potassium next. So okay, we have 2 potassiums now. Potassium's over here. That's just 1 potassium. So what coefficient do we need? 2. And now that that's, right, potassium's balanced, then I'll say, okay, acetate. Now we have 2 acetates. And then on the left side, we have 2 acetates. So it should be balanced. And again, you could set up a checklist. Right, lead, H3O2, acetate, potassium iodine. So we started with lead. Then we did iodine next. We did potassium, and then we did acetate. So check them off as you go along. And unless you change a coefficient that changes one of the other ones, you should be done there. But we can count these. So we have 1 lead on the left side. There's 1 there. We have 2 acetates, 2 potassium, 2 iodines. Same thing over here. It's just 1 lead, 2 acetates, 2 potassium, and 2 iodine. That's an I, 2. So it's balanced. Good? No questions? Perfectly clear? Easy? These are definitely good candidates for going back and trying these exact same ones without looking at any notes. All right, so not all of them will be like that. In fact, those will be harder level ones where you have to go from the names to the formulas and then balance it. Most of the balancing problems will be more like this, where I just give you the formulas. But it's good to review. Other questions? I'm here for the questions. Okay. So most of them will be like this, though. So we can just start from the formulas. Which one should we balance first? Was it? Yeah, hydrogen's a good place to start. Hydrogen is the only one that's not part of or doesn't have a corresponding free element, right? So if we start with hydrogen, on the left side we have 1 hydrogen, on the right side we have 2. So we'll go 2. You don't need to put lines in here like this if you don't want. Okay, so we have 2 hydrogens. So now we can look at oxygen and say we have 1 oxygen here, 2 oxygens here. So we can do 2 here, and then we'll just go back to hydrogen, right? So we change the number of hydrogens. So we'll come back over here, erase this one, and say, well, actually now we need 4 hydrogens. Oh, wait, that's not what I meant to do. This will work. Let's play it out. I meant to go to chlorine next. Huh? Well, because I went and did oxygen next. Oh, yeah, because I changed the number of hydrogens. Wait, hold on. But it was already 2. So this is 2. Oh, this is what it was, right, because we did 2 here. Then we went over here and said hydrogen's balanced. Did oxygen next. So I put a 2 here. So the hydrogen balances the oxygen. But that means that now we have 4 hydrogens. So we have to go back to hydrogen. Change this to 4. So now hydrogen's good, oxygen's good. I should do this. Hydrogen, oxygen, we do chlorine next. So hydrogen's good, oxygen's good. So we do chlorine next. And this needs to be, since we have 4 here, we need 2. So now that's good. The other thing you could have done is, instead of balancing the oxygens by putting a 2 here, you could put a 1/2. And then at the end, you would just multiply everything by 2. But if this is easier, do it this way. Try to avoid halves. And my laptop, hopefully that doesn't mess anything up, is updating Microsoft Office. Okay, so right, this looks a lot simpler. When it's just the thing, just balance this. A little easier. All right. So we're going to shift a little bit, talk more about what an aqueous compound is, or an aqueous solution. And it's a homogeneous mixture of a substance with water. And I think I'm correct to say that it's always going to be clear. So if you mix it together and it's homogeneous and it forms a true aqueous solution, it's going to be clear. You're going to be able to see right through it. It might be a different color, but you'll be able to see through it. It won't be cloudy. One of the key things here with aqueous solutions is that ionic compounds, when they dissolve in water, they usually dissociate into their component ions. So they don't stay stuck together. Because remember, something like sodium chloride, right, table salt, is not actually just one sodium and one chlorine. If you have a chunk of salt, it's this grid of all of these sodiums and chlorines in a matrix, all stuck together, clumped up. So we just talk about it as a formula unit. So the simplest whole number ratio of those. So when you put this into water, though, the water will come in and it'll actually go through and it'll pull out the sodium and chlorines, because the bond between the water and the chlorine or the sodium is stronger than between the chlorine and the sodium. So it's able to rip them apart and separate them into the solution. So it's a little cartoon, right? So we have a sodium chloride solution where the sodium and chlorine ions are dispersed homogeneously throughout the solution. These are also, if they completely dissociate, they're called strong electrolytes. They're called strong electrolytes because pure water doesn't conduct electricity. But if you put table salt in, it will conduct electricity. And that's why, actually, as I've mentioned a few times, you can put a 9-volt battery into salt water. You have to have salt in there. If there's no salt in it, you won't start splitting water apart into oxygen and hydrogen, because there's nothing to conduct the electrons. If you put a 9-volt battery into pure water, nothing happens. Similarly, if you had a light bulb connected to a battery and then 2 electrodes in the water, pure water, there'd be no light, but in salt water, there'd be a light. Of course, that applies up to a certain point. Like if you dropped a toaster into a bathtub, you're going to have a bad time. Yeah, or just don't do it. Well, why would you have a toaster next to your bathtub? You can wait for toast. Start it before you get in. So silver nitrate is another, it's another ionic compound, right? We have silver with a 1+ charge. Nitrate has a 1- charge. When you add something like this to water, we still get a strong electrolyte solution, but the polyatomic ions stay as polyatomic ions. So those clusters separate from the silver, but maintain their sort of general association. We do have compounds, though, that do not dissolve in water, ionic compounds. One of them is silver chloride. So silver chloride remains as a solid within the liquid water, and it doesn't dissolve because the bonds between the silver and the chlorine are stronger than the bonds that they can form with water. So it doesn't have enough strength, one way to think about it, to pull those apart. Yeah, we can do the rest of solubility super quick. A compound is soluble in a particular liquid if it dissolves in that liquid. Easy enough. Compounds are insoluble if it does not dissolve in the liquid. For ionic compounds, this is the next slide, we have a whole list of empirical solubility rules. So we talk about empirical formula. That's the formula you can determine from an experiment. You have to do more complicated experiments to get the molecular formula. For these solubility rules, they're empirical rules. So it's been observed that silver chloride does not dissolve in water, but silver nitrate does dissolve in water. I'm going to give you the solubility rules on exams. I'll give you the solubility rules on exams. You have to know how to use them. So compounds, this is like the same table when I took Gen Chem, and I don't like it. So these are soluble. Insoluble, generally. There are exceptions. This is the problem with empirical things sometimes, is that works most of the time, but also not all the time, because you're not explaining the underlying reason for why it happens, right? So this is like a solubility laws rather than solubility theory. So if you look at this list, we've got all these ions up here. For some of these these top ones, there are no exceptions to those compounds being soluble. So if you have lithium and any other anion, it's soluble. If you have nitrate and any other cation, it's going to be soluble. Chlorine, bromine, and iodine, however, they'll be soluble unless they're in an ionic compound with silver, mercury, or lead. And then sulfate is soluble unless it's paired with strontium, barium, lead, or calcium. This is why I hate these, because it's like, all right, these ones, but not some of them. You need to learn how to use this table, though, because I will ask questions about this.
So know this table?
Yes, know this table. So this is a similar thing going on over here as well. Oh, that line's not straight. We have hydroxide and sulfide. They are insoluble almost all the time, unless you have lithium, sodium, potassium, or ammonium, which you will notice, though, those are up here at the top. Those are the always soluble. And then sulfide when it's with calcium, strontium, or barium. Sulfide with calcium, strontium, or barium is soluble. Anything else is insoluble. And then carbonate and phosphate, again, always insoluble unless they're paired with these ones, right, these match, that are always soluble. Generally insoluble. Is there slightly soluble? Oh yeah, the hydroxide compounds, which are slightly soluble, generally considered to be insoluble. And then very quickly, is each compound soluble or insoluble? So for something like copper sulfide, we just go back to the table. So we have copper and we have sulfide. I don't think copper's on here anywhere. We found sulfide. So the only exceptions for sulfide, it's insoluble. And then we check over here, calcium, strontium, barium, we have copper, insoluble. Iron sulfate. Sulfate. I think there are a lot more anions in here than there are cations. So sulfate should be soluble unless strontium, barium, lead, or calcium. We have iron, so it's soluble. I think these are, or at least maybe when I did them, it was that it would go so fast that I wouldn't think about it enough and get them wrong all the time. Because they're easy enough. It's like, oh, I just have to check the table. But then you don't like pay enough attention. Okay, so the next one, lead carbonate. So carbonates, generally insoluble. And this is not one of the exceptions. Insoluble. And then ammonium chloride. Yeah, so ammonium. Yeah, ammonium chloride, yeah. So ammonium's always soluble. Chloride is mostly soluble, but because it's with the always, we know we're good. So it's soluble. Okay. We'll leave off there, and then we'll talk more about how you can use solubility rules to predict if it's a precipitation reaction on Tuesday.